Welcome to the fourth video in Section 7, Working with Graphs. In the previous video, we implemented test cases for streams. In this video, we will take a look at how to model advanced processing structures using flow graphs and how we can implement them. Let's start. In the previous videos, we worked with flows that have one input channel and one output channel, and we explained our streams as a linear sequence of steps, also known as flows. But not everything can be expressed as a linear sequence. So, to tackle this, Akka Streams comes with a graph flow. Graphs are needed whenever you want to perform multiple input or multiple output operations. Akka Streams currently provides some default junction implementations, which can be fan-in, many inputs, one output, or fan-out, one input, many outputs. The fan-in junctions are: merge takes n number of inputs and returns one output and picks randomly from inputs, pushing them one by one to its output. Merge preferred is like a merge, but if elements are available on the preferred port, it picks from it, otherwise randomly from others. Zip with takes a function of n inputs that, given a value for each input, emits one output element. Zip is a special case of zip with, which takes two input streams and zips them into a tuple of the stream. Concat concatenates two streams, first consume one, then the second one. Fleximerge enables writing custom fan-in elements using a simple DSL. And fan-out junctions are broadcast, which given an input element emits to each output. Balance, which given an input element emits to one of its output ports. Unzip with, which takes a function of one input that gives a value for each input, emits n output elements, where n must be less than or equal to 20. Unzip, which splits a stream of A, B tuples into two streams, one of type A and one of type B. Flexiroute, which enables writing custom fan-out elements using a simple DSL. Now, let's see the graph we need to implement. Here is our stream plan. We have a source that connects to a flow F1. Then F1 will be an input to broadcast the junction, which generates two flows, F2 and F4, which then merges to a flow F3 that will be an input for our sink. Let's implement this graph. Now let's define our source. Let's say we have an iterator from 1 to 10. Our sink will print each element. From our graph, we have four flows. Let's say F1 and F3 will add 10 for every element, F2 will multiply by 5, and F4 will add nothing. For now, we don't define new things. Now, let's define a flow graph. We will use a closed function from the flow graph object, which takes a builder block and returns a runnable graph. Now, let's define a builder block, which is a function that takes a builder of unit and returns a unit. In the body of this function, we will describe our graph steps. Let's revisit our graph. We will use broadcast and merge junctions. So let's define them now. We will use the add function from the builder instance to add broadcast, which has two outputs. And we will add the merge junction, which has two inputs. Now we need to draw our graph. So we will use graph DSL. The DSL is designed to look similar to how you draw a graph on a whiteboard. You use the arrows to connect various components of it. Akka Streams has graph DSL that enables to translate graphs from the whiteboard to a simple code. We use it via an operator, so let's import it implicitly from the GraphFlow object. So our graph will be in via F1 via broadcast, via F2, and F4 via merge, via F3, via out. We describe our runnable graph, but we haven't run it yet. So let's run it. Excellent! The results are as expected. At the end of this video, we implemented a simple graph flow and used just two junctions. I want you to pull our example and try other junctions as well for practice. See you in the next video, where we'll introduce Stream.io and of course implement it using examples.